Okay, let's get started. We're running a little late here. I have the pleasure of introducing Sarah. I usually get to say something embarrassing about students, but I didn't come up with anything for Sarah, which is the closest I have is, Sarah really, everyone who knows Sarah knows she cares a lot about everything she does. Too much sometimes. Maybe that's a little embarrassing, but she's very, and so it took her a while to find a thesis topic. She really wanted to really care about what she was working on, right? And you'll see that in the presentation. But I think the best I come up with on embarrassing is that when Sarah came here, the first few years, she really wanted to change the PhD program. She worked a lot to make some really good changes in it and stuff. But I think as time went on, she realized something which a lot of students don't realize when they come in. And she really realized it, which is the PhD program is going to change you a lot more than you change it. And I think that's true for all of us in many of the things we do in life. We go in there to make change, and it changes us. And I got to watch the changes. I'd known her for a decade. I knew her as an undergrad, co-term. She left for a while, came back and visited, and she was at Microsoft, and then PhD student. So it's been a real pleasure to have her here. I've been trying to recruit her as a PhD student starting like 10 years ago, and it's been like a few years to get her into the program. I think Manish helped me with that, because Manish knew her before she left. He helped me recruit her back. So it's been, there are very few students where you work with them and you just feel really good about it. A lot of times as a professor, it's frustrating. Like you're just always trying to make them better. But with Sarah, I always feel good, afterwards, and I feel really good about the thesis and everything else. Just that kind of thing where it feels rewarding, right? All the time I invested, I got back like time today. Take it away.
Thank you so much, and thank you to everyone for being here. Great, let's get started. Our hair reflects the people who came before us and the people who came before them. It's embroiled in our traditions and our cultural beliefs. Hair has started political movements and fueled protests. Hair can make us feel like ourselves and inspire others to be themselves too. In video games, these pictures are all really interesting. Feel free to ask me about them later. In video games, movies, and art, artists use hair as a way to tell us stories about their characters' personalities, their backgrounds, and their contexts. In this dissertation, I present a new framework for understanding hair in computer graphics that makes the creation specifically of curly and afro-textured hair, which the tools often don't support as well for in industry, to make these accessible, even to those without a strong or artistic background. And we have three primary goals. These goals are accessibility. We want to make sure that we're making something that anyone can use. Realism, we want to build hair that is grounded in reality, that's scientifically based, and diversity. We want to make sure that we can accommodate anyone and represent anyone. Our contributions specifically are a culturally informed and scientifically based hair taxonomy, a way of describing hair that is accurate to everyone. And encoding that captures scientific and cultural diversity. How is the computer going to understand the hair that we create? AI-powered solutions to determine hair texture from an input strand, a generative model for creating hair of all different types, and a texture transfer pipeline demonstrating the effectiveness of our methods. And as we go through, we'll start to see more of what these are, and they'll make more sense. Before we begin, though, I want to give a little bit of context to some of the terms that we're going to be using. First of all, when we talk about curls, we're often going to talk about a kind of helix that our hair forms as it curls downwards. And then in that helix, we might see a break. So what this is here on your left is a twist. There are moments where the hair will twist and it will just change the direction of its primary axis. And this is going to have disruptions in the helix. So when the hair starts to curl down, if a twist occurs, then that helix might change directions. What that looks like in a full strand is something like this, where you have these starts of a curl, and then it changes, and then you have a little bit more of a curl, and then it changes again. And on the full head of hair, that's going to look like sections where you see that there's curling, but different strands in the similar locations will curl in different directions because they both have twists that are pushing them in different directions. So you see less of that one single cohesive curl. This is an image that's been drawn over to show what we call a clump or a tuft of hair. This is really commonly used word in computer graphics, and it basically just means a section. So it's not as small as a strand, and it's not as big as your entire set of hair, but it's just a section of a hair that tends to move in the same direction at the same time. And this is going to be really useful because virtually this is often how hair is represented. On the left here, we have guide hairs, which is like a skeleton for the hair. You can see the directions that the hairs are moving, and this is how the artist will manipulate the hair and how it'll simulate. And then it's not until you actually finish and you're ready to take a picture that you put all the different render hairs on. Keep this in mind because throughout the presentation, we're going to be showing a lot of images that look like this. And it does look very unrealistic, and that's because these are guide hairs. They're not supposed to look realistic. Every hair here is colored a different color, and that's to show you, to make sure that you can see the differences between them. And then when we actually want to render that hair as real, we're going to go ahead and add clumps of hair for every guide hair to show it out in a way that looks more realistic. So in this talk, we're going to go over some existing work, what the state of the field is right now. We're going to talk about how we do things differently and build a framework that works better. And then at the end, we're going to show a text for transfer pipeline that shows you exactly how, that shows you some results of this method and finish up. So let's first talk about what strands are made of in digital space. Strands are points, strands of hair are points in XYZ space. So we see them here in 3D space, and they're connected by these lines. And then the single line is a single strand of hair, or a guide hair, depending on what you're doing with it. If you are an artist making hairs, what you'll probably be working with is something that looks like this, where you use nodes connected one after the other to change the hair into different styles. It's a pretty complex way of doing things, and people are extremely good at it, but it does take a long time to learn exactly how to do it. If you aren't an artist and you're working with virtual hair, you might be working with something that looks more like this, where you're playing a video game and you get to choose what kind of hair that your character had. You might have even noticed that finding curly and afro textured hair is a little bit harder in a lot of video games than finding straight hairstyles. So there's a number of methods that are out there. These are 4 different examples that try to generate hair from just an image. So if you aren't an artist and you're someone who's just looking to get a hairstyle, then maybe you can get one just by submitting an image and getting out a 3D set of strands. Unfortunately, these 2 often fail in the curly or afro textured hair case. So you can see here that there's like one big curl on this side of the hair, and it kind of disappears as it moves into 3D. This isn't uncommon in these styles. And I can talk a lot about why, and I'm happy to have more of that conversation. But one really high level reason is because in 2D, you can kind of see in straight hair, you can kind of see the direction the hair is going and follow it in lines in the photo. And if you trace enough of those lines and then you pop them into 3D, you can kind of estimate where the next hair might go. However, if you have a curly hairstyle and you trace the lines of directionality, and then you put that into a 3D space, it's much harder to assign a new direction for a new strand than it was in the first straight hair case. And as a result, the computer gets confused and it guesses what might be the right direction. And because these models are often trained on a lot of straight hair, it guesses downwards. And so you see that the end results are not necessarily good representations of the input image. And this is pretty common results across the methods that exist. We see that this person has curly hair, and then in the back, when it's trying to reproduce that, all the hairs that it's not able to see just kind of become stick straight because there isn't a clear direction that those hairs should be going. This method, as well as many other methods, are specifically focused on strand accuracy, which means trying to make sure that every strand in the final result exactly matches the strands in the input image. So now let's talk about our method and how we're going to do things differently. And the first thing that is really important to notice before we get into disentanglement and the meat of what we're going to be doing is that this is the same person on the same day with the same outfit, and their strands are in different locations. Strand accuracy is not our goal. When we turn our head, when a breeze blows, our hair moves. And we're not trying to get everything pixel perfect exactly where we want it. So what are we looking for? The primary thing that we're looking for are these lines of flow. this directionality of which way the curls go. So the direction of the hair strands in a curl might be constantly changing, but if that curl's going downward, the line of flow will just be pointing down. And this really helps preserve the volume as well. The other thing we're going to look at is hair texture. So is your hair straight or is it curly? Is it wavy? How big are your curls? How tight are they? This is all under hair texture. These things are fundamental internal constraints to your hair that won't change even as your hair moves around. These two things, flow and texture, are two separate but fundamental parts of hair. And we want to think of them as such. So for example, these people all have hair that is fairly straight at the top and then it starts to curl. You can imagine going to a hair salon and getting your hair cut and switching between one of these looks. These are all similar hair texture, but different flow. The hairstyle is completely different. Similarly, you can have the same hairstyle. These people all have bangs that are kind of swooping down on one side. Their hair is parted to the side, goes up, and then comes down again. And yet we recognize these hairstyles as all fundamentally different because they have different hair texture. So these two things can both be changed individually and completely change the look of a hairstyle. And now we can think back to our previous work and think about what this might have looked like if they had a concept of hair texture versus flow. If they had realized that the hair was curly, they never would have guessed the stick straight direction in the back because it would have been obvious because the front is curly that the back would have been curly as well. So let's go back to our guide hairs and our render hairs just to remind you that this exists as a final product and we're going to get there. But for now, we're going to dive deep into the guide hairs, look at the actual strand, and look at how we can separate flow from texture. So this is the goal. We will have our input strand, and this actually was a hair groom. We call them hair grooms, or like the 3D virtual styles, a hair groom made by an artist. And we want to separate that into the texture down here and the flow up there. So the flow we're going to see on the head, it's the direction that the hair moves around the head. And then the texture is going to be put on the negative z-axis. So we're going to take every strand and kind of just stretch it on the negative z-axis. And that way we can compare them all really well to each other. We want to be able to look at them and see, are these textures the same? Are they different? And really get a good sense of how they relate to each other. So how are we going to do this? We start by zooming in on the head and just picking a single strand. Once we pick the strand, we're going to extend it. So we're just going to add a little bit onto the end. This will help with some boundary conditions later, but for now, don't worry too much about it. We're also going to be putting some math on the side just to help for, if it's helpful for you. If it's not, don't worry about it. The next thing we're going to do is just take a low frequency sampling of this strand to get a basic center line. And this is just going to be an estimate of the center line, and you'll see why we say estimate later. Once we have our center line, remember, we want our hair to go down on the negative z-axis. So we're going to create a material frame on that center line and try to align our frame with the negative z-axis. The way we're going to do that is start by putting our strand at the origin, so putting it at 0, 0, 0. And then we're going to flip it so the very first segment aligns with the negative z-axis. Everything else is just going to rotate with it. So you can imagine if this is the first segment and we're trying to rotate it, we'll rotate this down and everything else just moves smoothly along with it. And then we'll do that for every segment until the entire strand is aligned on the negative z-axis. So this is what we end up with. And you can see now why we say this was just an estimate, because this result is actually fairly curly. We still see a waving back and forth. And the reason that that matters is because we wanted to disentangle style and texture. And we know the texture of the strand. As people, we can look at it and say, this is just kind of pretty much evenly curly the whole way down. But that's not what this reflects. So we want to make sure that we're actually extracting where exactly the texture and the style are differentiated. In order to do that, we're going to run an optimization that better approximates the actual center line of our strand. And specifically, we want to make sure that radius is changing smoothly. The radius can change through the strand. It can get curlier as it goes down, but it doesn't just suddenly jump from one to another. And that's what basically we're optimizing for here. Once we run the optimization, we give it a little bit of smoothing to make sure that there's no large jumps. And we have our new optimized center line. So let's go ahead and put that back on the head in the same exact process we did before, where first we move the root to where we want it to go, and then we align every segment to the segment we started at. And once we're done, we can get rid of our estimate. It's no longer useful to us. And we have our final style guide, which is our line of flow for the strand. We can get rid of that end. If you see the end tip has a little bit of a bias in the optimization, so we just get rid of that. Of course. And finally, we put our strand back in the canonical space using our new correct center line. So now we have our final strand, and you can compare our final canonical space strand with our estimate and see that it's much straighter. If you look down from the top, you can see that it really effectively captures the radius of the curl versus the other one that's a little bit all over the place. And we also have our final style guide or our line of flow. Now we can do that for every single strand and get our lines of flow and our canonical space texture. So this is another example, just again, strands that were created by an artist. And once we take those textures and we actually put them in the canonical space and can view them next to each other, it becomes much easier to see their similarities and their differences, which is exactly what we want going forward. So we talked about how to move a strand into the canonical space, how to separate lines of flow from texture. But once we've separated that and we have all our texture in the canonical space, how do we talk about it? How do we discuss it? And more specifically, how do we describe it? And so we can then create strands that are similar. There's a lot of different ways to do this. On the left, you'll see the Andre Walker hair typing system. This was a hair typing system that was popularized by Oprah's stylist. And this is a great, this is like really common. If you don't know about it, your friends with curly and afro-textured hair probably do. It's really great if you are curious about your hair and you want to go to the salon and get some hair product. But if you're looking to actually rigorously define and quantify hair type, it's not quite specific enough. On the other hand, we have something that is very specific. This is from a hair sciences paper, and it breaks down a lot of different ways that you can parse hair type. And it is really good if you have a scientist and you're trying to quantify all these different things about hair. But if you're asking people to define their own hair texture, if you ask them what their lipid content is, they probably won't have a good answer for you. This is way too intense to ask any given person to use to define their hair type. And so we're opting for something in the middle. We want something that is both rigorous and also easy for people to understand, and so people can input their own hair types. And the 5 parameters that we've been using, and we came to these in collaboration with hairstylists, with hair scientists, and people who work doing hair in computer graphics, so artists, are curl radius, wavelength, twist prevalence, thickness, and porosity. We're specifically going to focus on those top 3, which are the geometric properties. This tells you how the hair strand looks. The bottom 2 are really relevant for simulation, which is how the hair strand is going to move. But for the sake of time, we're going to talk about those less in this talk. So what are these parameters? Curl radius is pretty straightforward. You can take a single curl, put your fingers on either side of it, and divide that by 2. And that's your curl radius. If your hair is straighter or wavier and your hair doesn't form a complete curl, you can just follow the logical conclusion of that curl into a circle, divide that by 2, and that's your radius. If your hair is 6 straight, your curl radius is infinity. It's an infinite curl. Wavelength is very similar. You just measure the distance between 2 curls next to each other, and you have your curl wavelength. Twist prevalence is a little bit more, less numerically apparent. And so instead what we do is provide a chart, and you can look at this chart and identify where your hair falls. Remember, a twist is just a rotation around the axis of the strand, like this. And if you look at this first image, we see that helix we talked about that just kind of curls smoothly downward. There's no twist in the strand. The next one you see right here, it has a helix and then it stops, and then it has another helix. And that's where a twist is. We're looking for those points where there's discontinuity in the curvature of the strand. When we look back at this hair type that we saw earlier, a little bit blurry on the big screen, but you can see that the hair strands are pretty smoothly circular. They're pretty helical. We don't see a lot of twist. So I would put this down towards like a 0 or a 0.1. This hair strand, however, has tons of moments where the curvature is disrupted. We see lots of breaking points in that helix, so we're going to call this more of a 7.5. And the reason I bring these two specific hairs up is because smaller curls don't equal more twist. These are two different things, and sometimes they're correlated in hair type, but they're not the same property. So we have defined our parameters, and now we want to start generating strands. We want to start making new hair strands that have these parameters, because that's our whole goal, is making hairstyles. So how are we going to go ahead and create these strands? Well, our curl radius and wavelength are pretty straightforward. There are helix equations that allow us to use radius and wavelength to create a helix. When we want to add a twist, we just put in a moment and have the strand rotate around that twist. And then we're going to simulate the strands, which means just adding in the force of gravity, counteracting their internal forces. And this is what's going to really give us the interesting strand patterns. It's going to let us see all these sort of natural shapes that if you look up at the green here, so the green is the unsimulated and the brown is the simulated. And if you look up at the green, we're just not getting nearly as interesting and nonlinear expressions as we do in the post-simulated strand. For this, we're using the stable cluster outrod simulator, but you can use anything that works with curly hair. So let's say you have measured your hair and you are ready and you want to create hair strands that look just like yours. So you've measured, you have a curl radius of 1 and a curl wavelength of 1. So you create your helix with those measurements, and then you simulate, and all of a sudden the wavelength is at minimum 2.2 and the radius is at maximum 0.8. This is no longer your hair type. In order to make it simulate into something that's your hair type, you would know what numbers you needed to start with in order to get here. And that's a really hard problem, not only because simulations can be multi-stable, so this hair strand could fall in different ways depending on the conditions of the day, but also because thickness and porosity, like we talked about, weigh in on the simulation. So they change the way that the hair moves. Instead of trying to go back, find this inverse solution, and start with a strand that matches the thing that you want to end up with, we instead use an AI, a diffusion-based generation system, in order to directly generate the type of strand that you want to create. So we format our diffusion network as a unit with sinusoidal embedding of log s in our time, and we want to think specifically about what we're going to put into this diffusion model, because how we describe our strands to the model is really going to change how effective the model is at generating new strands. So one obvious thing we could do is position. We talked about the points being in XYZ space, so we could put those XYZ values into the diffusion model. But when even there's a slight perturbation at the top of the strand, we're going to see everything move. And these two strands, which initially are the same strand, would look very different for the model. So what do we want? We want some sort of representation of this strand that is closely related to our parameters. The closer it is to curl radius, wavelength, and twist prevalence, the more that the model is going to be able to capture and reproduce those things. We also want to make sure that they're well-defined computationally. Radius and wavelength are well-defined for helices. For people, as human beings, we can look at hair and kind of tell how far apart the curls are, but they're not actually well and precisely defined computationally. So we decide to use a curvature, torsion, and velocity-based system, and I'm going to show you right now why that fulfills our goals. First of all, radius and wavelength are tied with curvature and torsion. There are equations that relate these two values for a helix. You can see as radius goes up, torsion goes up, and curvature goes down. And as radio goes down, we see exactly the opposite. Same with wavelength. Both torsion and curvature go down when wavelength goes up, and they both go up when wavelength goes down. So we see that these two values are directly tied, which means that they're really, really proximal to our inputs that we want them to be tied to, but they're also continuously defined along the curve. And we're using a Frenes array basis for determining these values. Now, what happens when you put in twist? Because that's kind of, it's not, it wasn't part of our initial helical equation. Well, when we add twist, we get these spikes. And there are pros and cons. The pro is that there are the same number of spikes as there are twists. And this is persistent through simulation. We can literally count the number of spikes, and that tells us how many twists there are. There are 5 spikes, there are 5 twists. And so it's really, really indicative of what we're looking for. The con is that these spikes are highly noisy and that there are discontinuities in the spikes. And we're actually feeding something into the diffusion model. Discontinuities are a problem. So in order to fix this, we iteratively, every time we differentiate, because these are based on multiple differentiations of the curve, every time we differentiate, we're going to do a smoothing step that specifically addresses the problems that cause discontinuities in the Frenet-Serre frame. And when we do that, we get something like this, where the curve is continuously defined. There are still spikes, which is great because we can still count them and know how many spikes or know how many twists there are. But those spikes are clean and continuously defined. So now we have a method of converting our data into, we can convert our data into curvature, torsion, velocity in order to have our diffusion model perform well. And we can see just right off the bat, that works pretty well. You can see these are noisy curves that converge into curves that are, they were supposed to be the shape that they were trained on. And we can also see that it does something interesting. When we start with just as few as 2 curves, so this is 2 curls that have been input into the fusion model in green, and we get the rest of these curls out. And not only do they have similar radius wavelengths and twist frequencies, oh no, okay. But they also have a lot of similar properties. For example, over here on this first curve on the left, we see this kind of jagged back and forth pattern. And these curls were created by an artist, so this was just kind of how they were born. And we see that back and forth pattern repeated in a number of the strands, and the brown strands on the right. We also see this sort of hook-like feature at the top that we see perpetrated through, and another, this kind of messy figure 8 of a curve that's kind of staying in the same place while still curving that we see happening out in a number of these curls as well. So not only are we getting curls that are similar to the ones we put in, but we're also getting curls that are different. These are all, none of these are carbon copies of the 2 strands we entered. So once we have our diffusion model, we want to be able to actually tell it what radius, wavelength, and twist frequency we want. We don't want to just have to enter a strand that's ideal. We want to be able to put in our own values. In order to do that, though, we need to make sure that that the diffusion model understands what its current radius, wavelength, and twist frequency are at every step, so it knows what direction to move into. In order to do that, we have to build something that allows us to go from our curls over here, where we input curls, where it can actually then predict what the torsion, the twist frequency, radius, and wavelength are. One thing that's really important is that it's predicting a single radius, wavelength, and twist frequency per strand. But as you might have noticed, strands can change radius. They could start out straight and then become curly. What we're actually looking at here is the curve information from the bottom part of the strand. For me and for everyone that I've asked, when you're trying to figure out, how to parameterize your own hair and how to describe your own hair type, people pull their hair away from their face and they look at this bottom part of the strand. This is the part of the strand that is most characteristic of our hair type, and also the one that's easiest to see. And so when we're finding these values, we are specifically focused on that bottom part of the strand, like the bottom half. So in order to be able to determine these values from our input strands, we're first going to look at characteristic curvature. This one's pretty straightforward because the twist jumps actually don't affect curvature that much. They do affect it, but you can see by comparison, they're much smaller. By comparison to torsion, those jumps are much smaller. And so if we actually just take a low frequency version of our input curvature, we can get out a pretty accurate characteristic curvature that avoids all the twists that are imposed by, or all the spikes that are imposed by twists. For torsion, it's a little bit trickier. we built a model that takes in the curvature and the smooth curvature as an input, in addition to the torsion and a guess at the smooth torsion based on the parts of the curvature that are smooth. And we run a model to be able to estimate the characteristic torsion from that input. So specifically, we start with our strand, we estimate the characteristic torsion, and then we compare that to the original results. We have these original ground truth results because our strand hasn't been simulated, which means we know the numbers that it started with. For twist frequency, we also run a model, and this model basically is aimed to figure out how spiky is our curvature and torsion. So once we figure out how many twists are there, we can estimate a twist frequency. Once we have these, and we can run this model and get good estimates for twist frequency, torsion, and curvature, we actually want to be able to do that for simulated strands, not just unsimulated strands, because hypothetically, our diffusion model will be creating simulated strands. So we can then fine-tune this process on hand-labeled simulated strands. When we do that, we have to hand-label strands, which is more work, but we have to do it on relatively few strands because we've already run the base model, and it's the way that hair strands change curvature, torsion, and velocity is actually relatively small when we simulate. So we're able to bootstrap our approach and get good results from relatively few simulated strands. So now our model is able to tell what the values of its current strand is as it's creating a strand. And so let's say we want a radius of 1, but our model currently has a strand generated that has a radius of 0.5. Well, it's able to know that it needs to be bigger. So this red dot is going to indicate our current strand. And this black line represents the line of all possible strands. And the goal of the diffusion model is to get the current strand onto the line of all possible strands. Well, first, we want to take a step in the direction of all possible strands, but also now we know we want to take a step also in the direction that's going to put us on the part of the line that has the hair type we want. So we can then take a guidance influence step somewhere in between and end up with a strand that's not only realistic, but has the patterns we want. And we can see that that works pretty well. If we vary our target radius, wavelength, or twist prevalence, we get strands that adhere to the values that we've looked for. So at this point, our model can determine what kind of, can generate whatever type of strand it wants, but in order for this to be effective, we have to make sure we're training on a diversity of strands. We want to make sure that the data that we're inputting is really broad. And we start this by going back to the hair sciences literature. So this is a paper by L'Oreal where they took about 1,500 samples from people across the world, measured them on a number of different axes, and then did a PCA approach to get these 8 different buckets. So their claim is that there's 8 different hair types. And once they have these buckets, they can have examples from each down here. We're going to use these as a starting point to make sure that we have a lot of diversity in our training data set. But as we talked about buckets before, we want to make sure that we're not letting them be exclusionary. We want to make sure that even if someone doesn't fall into one of these buckets, if their hair is, maybe more unique, that they're still represented. So we take, in each of these buckets, we take a Gaussian-based sampling where we're more likely to get a sample within one of these buckets, but we also can get a sample from anywhere. And by doing this, we ensure that our training data set is not only diverse, but more indicative of hair types that are more popular. We also, in order to make sure that we have a range of types of data, we don't want all of our data to be coming from one place. We get samples from artists. So we commissioned artists to create a number of hair grooms. Again, that's just hairstyles in virtual space. And as we're doing this, we iterated back and forth with the artists and the people that the pictures were of to make sure that the artists' renderings were realistic and indicative of what they were supposed to be, or the people that they were supposed to represent. So we also trained on this data to make sure that we were that we were finding our data in different ways. So at this point, we have talked about how we can generate strands. We use a diffusion-based approach to generate strands of any input hair type. Now we want to talk about what we can do with that. So specifically, we create a texture transfer pipeline that can go from one hairstyle to another. So remember earlier, we talked about how people can have the same hairstyle, but different hair textures. And this is basically the goal of the next part of a project. We want to be able to take a hairstyle and change it into a different texture. The reason we want to do this is because there are a lot of hairstyles out there and available. There's a lot of work that's already been done, and there is a gap in what kind of hair textures those styles have been made for. So by allowing people to take a hair groom and change the texture into something that they're interested in, we make sure that people can generate grooms that better reflect themselves. So here's an example of the process that we're about to run through. Here is a hairstyle on the left that was created by an artist, and we changed the texture to a much wider curl, and we see the result of that on the right. These are the same exact style, but they have different textures. So let's talk about how we do this. We start with the guide hairs that are made by an artist, and this is the rendering, just again so you can see it and remember what that might look like. And we do the very first thing we talked about, which is disentanglement. We disentangle the center lines from the texture. So up top we have the hair flow, and at the bottom we have the hair texture. Once we have that, we want to think of a new texture that we want to put on. In this case, these are just some very, very basic wide curls that we create.
Very clever, isn't it?
One thing to note that's different about these two textures is that they're very different sizes. So the new texture is about twice as big as the old texture was. And you can see that when they're superimposed. So if we try to put the new texture on the lines of flow from the old style, we are going to get a lot of overlap that is not what we're looking for. So the first thing we want to do is pare down these lines of flow to about half. Now, how we do this is really important because we could just delete all the lines of flow on one side of the head, and that would be half the lines of flow, but it would not look the same. Instead, we want to be really thoughtful about which strands we pick. So you can see that there's two strands here that are highlighted in green. We cluster the hairs based on their location and direction. So we make sure that the hairs we are removing are similar to ones that are still there. And now you can see we have a pared down version. It's a little bit hard to tell, but if you look, for example, here, there's like 4 hairs coming out of the left ear on the side, and here you only have 1. And it's actually a good thing that it's hard to tell because we don't want to be able to tell. We want these styles to be still very similar. The next thing we're going to do is use our diffusion model to generate a number of strands that are similar to our inputs. Again, there's not a lot of diversity on the bottom because it's created from a really, really simple sample set. But it would be, so for these curls, which are again, really, really basic, it doesn't matter much, but if you have curls that are much more specific, if you see those same curl patterns copied across the entire head, it becomes really noticeable. So it's actually really important to get this diversity when you generate new strands from the model. And then you can go ahead and put those new strands that are generated back on the head. And we're back to what these two different textures look like. And we can see by superimposing their lines of flow that they do have the same style, even though their texture has been changed. Now we're going to look at some results. The one on the left is one of our results where the texture has been changed. The one on the right is a result from previous works that works less well. So again, we're looking at 2 styles that are the same, but the textures have been changed. And as these are turning, these are turntables, they're going to turn, take a look at some of the stylistic details that have remained. For example, sorry, the left one again is by an artist, and the right one is ours that we've changed the texture. Example at the top, there's these little hairs that are sticking up, and you'll be able to see them a little bit more as the model turns. There's also certain strands that kind of stick out in the back that you can also compare between the 2 heads. And also just notice that the shape and the directionality is the same between the two. Here's another result, and I just want to go do another turntable so you can see how the guide hairs relate to the render hairs. So these are both hairstyles that have been generated using our method. Or sorry, this is one hairstyle that has been generated using our method, and here are the guides and the render hairs for it. Here was the initial style on the left and our changed texture on the right. And here it is, both are overlaid with the guides. One nice thing about making sure that we're using guide hairs instead of render hairs is it means that these can be put right back into artist pipelines, so they can be simulated or used for characters or whatever use case you would like with the final strands. So now what we're going to do is these are 4 completely different models that were made by artists, and we're going to look at them all changed into the same texture. So we're looking at different styles, same texture. First, straight hair, just to be like, really easy to start with. You can see that these are all straight hair versions of the same style. Now we're adding on a very coily hair texture. You can see these are distinct styles that all represent the same texture. This is a wider curl that has a lot of twist in it. And these are all rendered the exact same way, just so it's easy to tell the differences. And now I want to do the opposite. We're going to do same style, different textures. So here we have the artist input on the far left on the top, and the four different textures applied to it. One more of that. Just kidding. Another one of that. And then lastly, I want to look at just how we can add this on to existing work. So there's a lot of existing work that specifically we talked about fails in the curly and afro textured hair case, which means that the styles they're creating aren't necessarily bad, but they're not creating the curls that they should. So this is an example from a paper called HAR. That's a text input to generated hair. So if you put in the input prompt voluminous afro textured hair, you get out these 2 styles. The curls, if you look at them, are like lightly wavy, but these are not by any means afro textured hair. Even the one on top, which is a little curlier, is mostly like 1 curl per strand. What we can do is we can use our texture transfer pipeline to decide what texture we want and overlay those onto the curls, which gives us something that's much more natural looking, even in the same style. So you can use existing methods to generate hair, and then our method to actually change the texture to something representative of what you're looking for. And here are the rendered versions of that output. All right, conclusions. As we've gone through, we've talked through a lot of different things, and specifically, I presented a culturally informed and scientifically based taxonomy. So we talked about how we describe hair strands, radius, wavelength, twist, porosity, and thickness. We discussed it in coding, curvature, torsion, and velocity that captures scientific and cultural diversity and how that relates to the properties above. We discussed AI-powered solutions to determine hair texture from an input strand. Given a strand, we can tell what its properties are, and then a generative model for creating hair of all different types. And finally, we showed our results via texture transfer pipeline demonstrating their effectiveness. And I want to go back to this previous work that we talked about at the beginning, where you see the curls kind of disappearing into these 6 straight lines. And think about how, I think one of the things that feels the most salient for me is how even bringing this knowledge and the idea that we can separate texture and direction and separately implement them, how much this would change existing works just by implementing that framework. Because for here, for example, we would have curls because we would know the hair texture, and so we would know at least at a baseline what it should be looking like. And the goal for this work is that not only will it be able to help, anyone who doesn't have a strong artistic or technical background to be able to make hair that they feel is representative, but also make it cheaper and easier for people in various industries to be making these hair types. And then I want to end on one thing that felt more and more salient as I moved through the project, but it's just how this feels like it expands to other concepts in computer graphics. Even though we were really focused on hair during this process, there are all these things that we learned that feel like they are the bases, not just for hair, but for how things that we care about can be represented and can be reproduced virtually using AI tools, while making sure to capture and utilize all the scientific learning and cultural background that we have in the world around us. And so the first thing that we did, and that I can see doing in the future for a different topic, is using this social understanding and perception to figure out which things in the phenomenon you're navigating are the same and what are different. What can be disentangled, and when does that actually clarify creation? Secondly, create a relevant canonical space. What of every different aspect that you disentangle, what is important about it, and how can you isolate that important thing? How can you parameterize, not just based on the math of what you're seeing, but also on the social and cultural norms that determine how other people see that same phenomenon? What way of talking about it best connects the people that you're talking to and the computer that you're using to create? And finally, being able to generate and combine these aspects separately. Thank you so much. Can I do questions before now? Oh. Oh. Can I do that after the questions? Is it okay if I do after questions? Okay, we're good. I have slides. Sure. Sorry. Mm-hmm. Yeah. Oh yeah, absolutely. So working with the artists was really, really interesting, really exciting. So basically, as it stands, there's no realistic database of curly and Afro-textured hair. And so we've started compiling the first one. We have a number of grooms, and we're still working with artists to make that data set even bigger, and that's going to be published for just like general consumption for free. All the artists are paid courtesy of the Magic Grant, which is very exciting. And it's been, yeah, really, really cool process to be able to sort of go back and forth and learn a lot from them. The way that we work with the artists, so we started just by giving them pictures, and then they would give us back a groom, and then, or I would then comment and say, oh, it looks like this is a little off or that's a little off. And I didn't feel like it felt weird for me to be the expert telling them this should change or that should change. So then we started getting the community members involved, where we would take pictures of people who were interested in being able to then use a 3D groom to put into a video game or have themselves. And they would work with the artist. So they would say, this doesn't feel like it represents me, and work to get a groom that they felt like fit them. And then they get a room for free, which was kind of the upshot of doing that emailing back and forth. So that was really fun to do that work. Yeah, thanks for asking. Yes. Yeah. Mm. No, that's a great question. Yeah, absolutely. I think there's like a loop, I think, where academic work gets published in journals, and then people at various companies use the work in journals to improve their own work, but also there's research being done at companies where they will do work for their own video games, movies, whatever it is, and then they'll publish that work. So there's definitely a lot of different avenues for that. But yeah, I think the goal is that everyone's just kind of putting out their next step and next step, and all of that is kind of coming together into the programming that is hopefully not only used in industry but also open source, so made accessible and used by everyone. Thanks. Yeah. Mm-hmm. Mm-hmm. Honestly, so that's why I was really excited by the so you have the kind of two options with the diffusion model where you can give it a set of parameters and say I want a curl that's this radius and this wavelength, etc. But you can also input your own strands. And I think that pipeline actually feels really exciting to me for that reason. You can make strands that are super specifically weird, like strands that are like straight and then start curling and then are straight again, or like any sort of like weird specific um, thing you want to capture for the story you're telling, and use that to generate a number of strands that have that diversity. And so it doesn't look like you just like made one strand and copied it all over the head. So they have diversity, but they also are like representative of that meaning that you tried to infuse. Yes. Yeah, absolutely. I think that like that specifically is something that I've been really thinking a lot about, and I would love to build this into. I think a lot about how in the really advanced character creators you have so many weights and so many blending tools, and then in hair it's like you have one or the other. But it feels like actually disentanglement means that you can blend really easily because textures you can blend textures. You can make a hair slowly get longer or get more curly or tighter, lighter. So I think that having the textures separated enables blending like that in a way that I think would be really fun. Yeah, probably in the texture space. So in like the canonical space. But I mean, ideally, and I think it actually allows you to do blends in both because you could do a blend in the texture space that's changing the type of hair at the same time as then you have another slider that's a blend in the world space where you just have the lines of flow and you blend between, because then it's just a simple direction in world space, like which direction is the hair going? And you can blend between two different directions. You can blend between two different styles even. So you could do like both of those things at the same time and then merge them whenever you want. Yeah, I think that's a really cool application direction. Oh, okay. Um, They haven't specifically tried my method, but they've looked at, so I've run results by a number of the artists and was able to get really good feedback, which is cool. So that was one thing that I started doing in the last month or so and don't have like enough structured feedback to be able to put it together in a chart. But that's something that I'm aiming to be able to do soon. And not only have gotten really good feedback, but also got really cool ideas for future work. So yeah, it was, yeah, good stuff there. But no, I don't have anything. I haven't actually like let them sit because I have to make my code prettier first. And yeah. Maybe Callum, sorry, I missed you like 3 times. Mm. Yeah, definitely. So it started with reading a lot of hair sciences papers and kind of whittling down. I mean, there was both the like whittling down things that we don't actually need because they're not relevant to how hair like looks from a distance or like looks from this distance. But then also ones where they were redundant. So I think one that we looked at that was interesting and we debated for a while was like the axial thickness. So hair isn't always, if you like cut it on its cross section, it's not always a circle. It can be flat. And actually, animal hair gets really weird cross sections, which is fun. But human hair, it tends to be flat or circular. And so a lot of people, when they're talking about hair, they'll not just say thickness, but they'll say thickness in 2 directions. So that's one that we were thinking about. But the fact that hair being thicker in one direction than it is in the other direction is basically to increase the curliness because there's less structure in one direction, so it'll curl in that flatter direction. And so basically after thinking about it for a while, the thickness is actually kind of redundant with the radius and wavelength, which you already have, which are the properties that come out of that. So we ended up just using thickness itself is like an example of a thing that changed. But it was a lot of, so we did the hair sciences and then a lot of like, I spent a couple days in salons just like talking to people, which was really fun. I did have to pay for a haircut to get that privilege, but it was worth it. I went to a hair sciences conference, talked to people there. So there was a lot of talking with experts to really, and most of that was just, here's what I'm thinking, tell me where that's wrong, and iterating based on that. Yeah, it wasn't my finest moment. Okay. Can I do a quick acknowledgement? All right. So I want to start by thanking my committee. So first and foremost, Ron, thank you for not only teaching me how to do research, but teaching me really thoughtfully how to be a better mentor and how to be a better teacher and how to exist in this world in a way that was going to get me to where I want to be. Brian, thank you so much for sharing. I really appreciate, I interacted with you most in Graphics Cafe, and I really have appreciated how thoughtful and perceptive your questions always are. And you're interacting with a lot of concepts that are like wildly different. And I really admire the like energy you bring to that. And it's, yeah, evocative of the type of academic I would like to be going forward. Thank you, Manish. You, as Braun mentioned, I've worked with you since undergrad, and you've really helped me develop my ways of thinking about how the work I do exists in the real world and how it affects people and how I can make sure that I'm best serving the people that I want to be serving. So thank you for that. Karen, I've always really enjoyed our conversations. And also, as I've started doing more mentorship in the past years, I've really learned a lot via your students about how you mentor. And really, well, it's not to sound creepy, but I really I've learned a lot about how to be a mentor in in the structural things that I hear for you. You're very thoughtful in how you do that, and I really appreciate that a lot. And Kayvon, I've also worked with you since undergrad, and you have been there as a mentor like many different times when I've had questions not only about the work that I'm doing, but also like navigating the structure of academia, and really taught me a lot about that process and about how to like move forward into the future that I'm looking for. So thank you. I also have had a lot of great mentors outside of these 5 people. So specifically Daniel, Pat, and David, and Pat is here today. He's very sweet. These people are, why I went to grad school and really like convinced me that this was a path that could be for me, which I really appreciate, and this is really life-changing, obviously, because I'm here. The people on the bottom, Stephen, who's also here today, just as specifically in this project and in hair, in addition to being a great advisor for when I was at ILM, has like helped me in maybe 50 different ways on this project, in how I am thinking about the problem, how I'm understanding how artists work in industry, when I'm developing the directions I want to go in. Just really, really appreciative of everything that you've done. And then Sean was my manager at Microsoft, and Bill is my manager at Pixar. And just, I feel so lucky to have had such an incredible suite of people directing me and teaching me throughout this process. Thank you to the Brown Institute. This grant was not only helpful because it helped kickstart the project that I was answering Purvi's question with, of being able to actually work with artists without taking advantage of their time, but it also just introduced me to such great people and a culture of really like thinking deeply about the systems we're in, thinking about how to make them better. I'm just really appreciative of the group and the people I've met through it. And the other groups that I've gotten funding from that have all just been like full of amazing people. And I feel a lot of gratitude for being able to talk to them about the more complex parts of my project that aren't related to computer science. Specifically, I wanted to thank people in DARE. This fellowship has been like a real rock during the last couple of years of the PhD, and I'm so thankful for this community that's so easy to be honest and vulnerable with, and really grounded me throughout this entire time. I've had a lot of experts in various spaces that have volunteered their time and energy to the project. So on the top, we have people, the top 2 rows are people in the computer graphics, hair, art world. We have people who work at salons who have talked with me and helped me, and people in the hair sciences space that have just like, their knowledge and expertise has been invaluable in this entire process. The students that I have gotten to work with have been so much fun. I think I didn't do a lot of mentorship for the first few years of the PhD. And then when I started doing it, I was like, wow, I can't believe I haven't been doing this the whole time. It's one of the most fun and meaningful things that I've done in the PhD. And I just like have so much love for all of these people. My lab mates, I feel so lucky to have come into such a lab with such strong culture. It's been very sad as people have graduated, but it's been really fun and great group of people. And then I probably spend as much time in my lab these days as I do working in coffee shops. And the people in those coffee shops have been like so nice to me and so kind. And like, I don't know, just feels like a second office. Ashley at a coffee shop near my house ran through my slides with me last week. They're just like really, really been great and kind people. To my friends, so many of you guys are here, and I just love and appreciate you all. And I know sometimes, especially in the last couple of years, I've been disappearing, but I hope to disappear less now. And I really appreciate your patience and your support and your love. And then specifically all my housemates, I've gotten to live with a lot of really, really incredible people over the past few years. And going back to a house that is full of people who care about you has just really made everything better. And then these are my high school friends. So these are, I think, the people who really like shaped me as I am today. And I still talk to all the time, and I really love, and I just like wouldn't be the person I am right now with not like, it was really, my personality was developed in high school, and I really am grateful to them for that. My computer graphics friends, most most of whom are in the front row. This PhD has just been a process of mostly spending time with these people, and it's been so lovely for it. And then specifically the people that I have had since like day one of the PhD over Zoom in 2020. This PhD has been like a group project, and I am so lucky to have found you guys so quickly. I still like can't believe that happened. To my family, and also Josh's family, all of whom have been so supportive and kind, and just made the moments in between all the work feel so much fun. And again, people I haven't gotten to travel to see as much as I'd like in the last year, but I'm really excited to make more time. Specifically my grandparents, who are who are just the most loving and supportive people in the world. My grandparents are here, and my grandparents are in Zoom in Chicago. My siblings, both of them came out, who are so much cooler than me, and so wonderful, and just like always are fun, always are funny, help me remember not to take things too seriously, and then support me when I need to. My dad, who is able to come out. I really looked for a nice picture, but he doesn't take those. This wasn't his graduation. Who also always reminds me to relax and take care of myself and not take anything too seriously. And my mom, who is always supportive. This is a picture of her supporting me when I had a breakdown about a month ago, and who's just always ready to listen and always ready to talk, and just, yeah, wouldn't be here without any of my family members. And lastly, to Josh, here's a picture of Josh supporting me after I had surgery, who also has been like doing all of the cooking and cleaning and everything that's necessary to keep me alive for the past month. And yeah, I just, and also is fun beyond doing all the chores. And I also, yeah, just learn so much from all the time. So thank you, and thank you all for coming. Yeah, really appreciate it.